Hello, everyone. Welcome to this symposium. So, as all of you know, the fronto-parietal network is one of the most important network in our human brain. And the fronto-parietal network cooperated with the attentional network or the default mode networks. So how these networks cooperate to work in our daily life or in various cognitive tasks is an interesting topic. So today, it's our great pleasure to have three excellent speakers here to discuss all these questions. Our first speaker is Professor Sabine Kastner from the States. So today, Professor Kastner will give us a talk about the neurodynamics of the primate attention network. So please, Professor Kastner.
Well, thank you very much for inviting me to this really exciting symposium. Even though it's online and recorded, I think this will be a very exciting thing for everybody to attend. Now, let me start by introducing you to one of my favorite artists and pieces of art. This is René Magritte's The Human Condition. What this scene or this painting has in common with other natural environments that we typically navigate is that it contains a lot of objects that we cannot process all simultaneously or at once. And what we typically do to reconstruct scenes like this is to recruit a spatial selection mechanism, which we sometimes refer to as a spotlight of attention in our textbooks. This spotlight operates across small regions of space, and whatever falls into the spotlight will be preferentially processed. Now, we can move this spotlight across the scene to reconstruct it. And in real time, this happens much faster at a rate of about 20 hertz, so every 50 milliseconds or so. Importantly, the spotlight can be moved in what we call a covert way, so without executing eye movements. And I will tell you today about the neurobasis of the spatial selection mechanism and of the covert form of it. And I will refer to this as attention today in my lecture, but this is just, for a handy abbreviation. Now, let's take a look at what happens in a human brain. Let me just start this. During attentional selection from spatial locations of the kind that I just outlined. This is from a functional magnetic resonance imaging study. This is an inflated cortical surface. We are looking here at the right hemisphere. This is the occipital pole. And I don't know why this stopped now. Now it goes again. Okay. This is the occipital pole. This is the frontal pole. And what you see here is a buildup of fMRI signals first over the occipital pole. So that's in the visual system proper, if you like. And then a later build up across the opened interparietal sulcus, so in posterior parietal cortex here, and there are also activations in frontal cortex that we cannot appreciate in this bird's eye view that we have on this right hemisphere. Now, what the remarkable thing is here is that even with a very simple cognitive operation like the spatial allocation of attention, we activate a large-scale cognitive network that spans a multitude of nodes, and that those involve all major lobes. Now, what we are interested in is to understand the computations that each single node is performing, and importantly, how these nodes interact across the large-scale network. Now, in my lab, we are studying the neurobasis of selective attention using two primate brain models, the human brain that you see on the left and the macaque monkey brain on the right. And we do that in a comparative approach. we first establish behavior in the two species by using tasks in cognitive psychology that have been well characterized in the human. And I will give you examples for this approach in my talk today. Then we relate behavior to neural signals that we obtain with intracranial electrophysiology in both species. In humans, we work with epilepsy patients in collaboration with Bob Knight from UC Berkeley and Joseph Pavizzi from Stanford. And I will introduce you to this technique later in my talk. In monkeys, we use neuroimaging methods to identify multiple interconnected sites across a large-scale network that we simultaneously record from. When I introduced the spotlight of attention to you earlier, I told you that we can move the spotlight dynamically across the visual scene, but once it is allocated, what we perceive subjectively is that we take the information that falls within that spotlight in continuously over time. Now, in my talk today, I will show you that this is just an illusion. What really happens is that the spotlight blinks and goes through phases where we can read out more information and phases when we read out less information. And these alternations are rhythmic and they are associated with better or worse performance. And I will tell you today about the neurobasis of these rhythmic properties of spatial attention. Now, let me start with a behavior that got us into these rhythmic properties. And this is work that Ian Fiebelkorn has done in my laboratory. He has now his own laboratory at the University of Rochester. Now, we used a task from human cognitive psychology that is known as the Egli-Driver task. Now, what's going on in this task is that our participants are fixating centrally. So then they will never move the eyes in this task. Then there are two bar-shaped objects that can be presented in this vertical orientation or in an horizontal orientation that will change from trial to trial. Then there will be a cue presented in one of the four corners of these objects. So in this example, it's in the upper right. This will be followed by a variable cue target interval that can last up to 1.5 seconds roughly. And then there will be a target shown at threshold. So this will be much less bright than it is in this demonstration, with a high probability, with 80% probability in that target location. Now I show you just here a summary of these different epochs and events that are happening in this Egli-Driver task. So it's a very classical spatial attention task. There's a few other twists, but I will not go into them because they are not relevant for this talk. Now, what interests us specifically is the cue target interval. This is the interval when attention is allocated after the spatial cue here at this location. So it's allocated up here in the upper right at this moment in time and throughout this period. But there is no further change in the sensory environment before the target appears then. Now, when we simply plot the performance of a human participant here, or of a group of human participants, as a function of this cue target interval, this is the change in hit rate here, we see something really remarkable. So instead of being flat, basically, and showing a continuous performance at some level, what we see here are these ups and downs in performance. So, and they coincide with certain time windows. So for instance, at this time window over here, at this time period of a cue target interval, just 420 milliseconds or so, you see that our participants are about 5% or 6% better than about 120 milliseconds later. So they go through these peak performances and trough performances, and this alternates and goes back and forth. So there's a behavioral rhythm here that goes at about 4 hertz, sometimes up to 6 hertz. So that changes a little bit from participant to participant. But this is the average. Now, when we started these studies, I was very skeptical whether we'd see these behavioral rhythms in old world monkeys that we also study, as I told you. And these monkeys are about 20 million years older than our species. So we deviate about 20 million years. But to my surprise, we saw the same behavioral oscillations. These are now examples from monkeys here of these oscillations. Again, the hit rate as a function of the Q-target interval. In this ugly driver task, not only the peak frequency of about 4 hertz is similar, these peaks and troughs of behavioral performance are remarkably aligned in time. Now, given that these rhythmic properties of attention have been preserved during primate evolution, we thought that they may be of fundamental significance for this cognitive process, and therefore we wanted to understand the neurobasis of these rhythmic properties a little better. Now, let me first summarize these behavioral studies by saying that behavioral oscillations at 4 to 8 hertz occur during visual spatial attention, setting up alternate states of better or worse performance, and the rhythmic properties of attention are preserved throughout primate evolution. So let me now tell you about the neurobasis of these rhythmic properties, and I will actually start with our human intracranial studies. These were performed by Randolph Helfrich, a postdoc at the time in Bob Knight's lab at UC Berkeley. Randolph now has his own group at the University of Tübingen in Germany. Now, in electrocorticography or ECOG recordings, epilepsy patients get implanted with ECOG grids. You see here 2 intraoperative scenarios of implantations of a denser and a less dense grid here. These implantations serve diagnostic purposes to prepare the patients for neurosurgery to remove their epileptic tissue. So there's absolutely no scientific goal regarding the implantation sites. And for that reason, we see quite variable coverage from patient to patient. I show you 4 examples here. Now, when we combine recordings from several patients, that is what we typically do, we get a really, really remarkable broad coverage across typically the left hemisphere that's targeted by these implantations. Here you see these combined recordings across 8 patients in this case. So this is a lateral view, a medial view, and a posterior view. And these are about 800 electrodes we can record from here. And you see that we get very nice coverage across this hemisphere with a few exceptions in this particular example. Now, what we typically do is that we combine these, so we render these electrode recording sites onto a standardized brain and then combine it with different atlases. Here you see an atlas of the human visual system that we created in my lab from retinotopic mapping done with fMRI. But there are many, many other atlases that you could use. But what these atlases do is really to help us locate some of these some of these recording sites more clearly. Now, the signals that we record with ECOG are intracranial field potentials. So you see a raw potential here for, a trial in the beginning of a trial here in our Egli driver task down here. And what we can do with the signal, so this signal is fed by thousands of neurons that are underlying these electrodes here. So these are relatively large electrodes. They are much coarser than what you may know from monkey electrophysiology, where you can target single electrodes. So these electrodes don't do that. They record field potential that is fed by thousands of neurons underlying this electrode. What we can do with the signals, we can filter it along different frequency domains here. So again, this would be a time from the Q onset in our Egli driver task. And the signal that I will particularly focus on here for these human ECOG recordings is the signal here of high frequency broadband signal above 70 hertz roughly, can go all the way to 200 hertz or so, depending on where your cutoff is with the recordings. And this signal is so powerful that we can even study single trials, which is typically very, very difficult, for instance, in monkey recordings. Now, I will show you a single trial from one patient, and the recording site is here in the posterior parietal cortex in the Egley driver task. So here again are just the different epochs that happen in this task to remind you. So here are the high frequency broadband signals that we obtain. This is the Q onset. There's a Q evoked response. Then here, the gray denotes the onset of the Q target interval. Again, this is a pure attentional or cognitive state during which there's no change in the sensory environment. The broken line here denotes the target onset. Again, this is at threshold, so it will not evoke a strong response. And then the green line here is the motor response, which is a button press. Now, what you can see here right away is that during that Q target interval, there is a strong fluctuation going on of this high frequency broadband signal. And this seems to be rhythmic. And I want to convince you that this is not our best single trial that we obtained, but this is a very regular finding. So here are two other trials from the same patient and the same recording site with different Q target intervals. And you see these fluctuations in every single one. You see it also in this one. This is a kind of interesting case because here the subject is missing the target. And I will get back to that later. So the first question that we had was, what is the frequency of these neuronal fluctuations of the high frequency broadband signal that we see here? And we did a peak triggered average to get at that. What we do here is that we take these peaks and we take the 500 milliseconds before and after, and then we move one peak over and so on and so forth and average across a lot of trials. And excuse me, what we see then is this. So we did this on the raw field potential. This is the black line here, and then we fit sinusoid. And you can see very clearly in this 1 second time window here that we are looking at a 4 hertz rhythm. Now you have a neuronal rhythm that goes at 4 hertz, and you have a behavioral rhythm that goes at 4 hertz, but that does not mean that these rhythms have anything to do with each other. It could be just a pure coincidence. So we wanted to see whether we could link the behavior more closely to this 4 hertz rhythm. And the analysis that we did, I want to introduce more intuitively. We looked at the relationship of the detection performance relative to when in that 4 hertz, in the phase of that 4 hertz oscillation, the target appeared. So in this particular case here, in this trial, and we did this again on a single trial basis, we see that the target appears close to the peak of this oscillation. This is also true in this example here, but in this example where the subject is missing the target, we see that it appeared close to a trough of this oscillation. Now, if we do this again systematically over many trials and many recording sites, etc., what we see here is what we call a phase detection relationship. So this is the phase of this 4 hertz oscillation, and this is the hit rate. And you can see that there's clearly a phase associated with worse performance that is flanked by better performance. So the phase of this 4 hertz oscillation, 4 hertz is often referred to as a theta oscillation. The phase of that theta rhythm in the brain informs about behavior and is predictive of behavior. So if we look at these phase detection relationships systematically across the different recording sites, this is just one patient here. Red denotes a strong phase detection relationship, so a strong difference between a trough and a peak. In that phase detection relationship, we see that This is a specific relationship that is very, these relationships are found in frontal and parietal cortex, not so much in other parts of, like in motor cortex and so on. So this is a property of that fronto-parietal network that, that we introduced to you in this symposium. Now, let me summarize this part of my talk by telling you that high-frequency broadband power was modulated by theta oscillations across the fronto-parietal network, and that target detectability depends on theta effects. So here we can, I think it's one of the rare examples where we can use intracranial physiology to link oscillatory signals in the brain to performance. Now, we wanted to see whether we could also study these signals in the monkey, and whether we could probably also get a little bit more specific information about the neural basis with the many opportunities that this particular animal model offers. And again, this is Ian Fiebelkorn's work. So since we had seen in our human recordings a very strong engagement in rhythmic properties of attention of the fronto-parietal network, we decided that that was our starting point for recordings, and we recorded simultaneously from the frontal eye fields in frontal cortex and the lateral interparietal area in posterior parietal cortex. Now, these two areas are heavily interconnected, and they are embedded in at least two functional circuits that are reflected in the single unit activity that we can measure in these two regions. The two functional circuits are a sensory or visual processing circuit and an oculomotor circuit. We find neurons in these two regions that are purely responding to visual stimuli. Here is an example. So there's a good visual response, but not a response during a saccadic eye movement. Then there's the opposite. There are movement neurons that are not responsive to sensory stimuli at all and respond only during eye movements. And then there is a mix of the two of them, so neurons that respond to both. Now, these neural circuits are in potential conflict with one another, because if you want to process sensory information, you shouldn't move your eyes. And if you want to move your eyes, or you need to move your eyes, then you cannot process sensory information. And I will show you today that the rhythmic properties of attention, this theta rhythm, is an important mechanism to coordinate these functions and to avoid the functional conflict. So how did we get there? So let me just start by establishing the behavior. So these phase detection relationships that I'd shown you in the human brain, that was our starting point to look for them in FEF and LIP. And what we expected, this is again the hit rate, this is the phase of our peak theta oscillation in these regions. We would expect a relationship like that with a peak and a trough, with a good phase with better performance, or a poor phase with poor performance, instead of something like that that's flat and not predictive of behavior. And we looked at that in the local field potential, which is similar to the field potential that I've shown you, but it is more localized in the human brain and fed by fewer neurons. And indeed, we see these phase detection relationships. So a 5 Hertz theta oscillation here is predictive of behavioral performance in the frontal eye fields and also in the lateral interparietal area. So we basically establish what we have seen here in the human brain as well. And I told you already that these constitute a good and a poor phase with relation to behavior. Now, in these monkey data, we can also look at higher frequencies. That is more difficult due to the amount of data that we can collect in ECOG patients. This is more difficult in human patients, but in our monkeys, we have a very large data set and we can look at higher frequencies. And so we wanted to know whether higher frequencies also set up these phase detection relationships, and if so, whether they would be associated with the good or the poor theta phase. And what we see here is that in FEF, we see a very prominent beta activity that is also predictive of behavior. And it is exclusively associated with the good theta phase, so it predicts good behavior. There's nothing during the poor theta phase. In LIP, we also see higher frequencies associated with the good theta phase. And this gamma activity that we see here is also, again, sets up phase detection relationships. So gamma phase can predict behavior. And interestingly, in the poor phase, we see very prominent alpha activity, but it is predictive of poor behavior. So now, since I do not have a lot of time to show you all the neural data, I just want to summarize what we got thus far schematically here and fill in a few more bits. So here's our theta oscillation. I did not show you, but you can take my word for it. You see it in both in FEF and LIP, and it is phase synchronized across this network. Now we see that there is beta activity prominently associated with the good theta phase in FEF. And there's gamma activity also associated with the good theta phase in LIP. And these faster frequencies are actually coupled to the theta oscillation. So theta is controlling the power of this fast oscillation here. So the power will go up, will be very strong during the good theta phase and not very strong during the poor theta phase, and so on. And then we have this alpha activity here in LIP, and I will not talk much about it. If you like, you can ask me a question about it. So what does this all mean with relation to function here? What was revealing in our analyses was when we were now looking at the spiking activity of individual neurons relative to this oscillatory activity that we get from the local field potential, so from a population signal. And what we saw was when we looked at the spike field coherence, so at the coupling of spiking activity to different frequency ranges in that local field potential, we saw that the visual neurons in LIP were coupled with gamma activity within LIP and also in FEF, and that indicates that LIP spiking activity uses that gamma frequency band to route information into FEF. On the other hand, the movement neurons in FEF, the spiking activity of the movement neurons was strongly associated with beta activity, both within FEF and also in LIP, again suggesting that that beta activity is using that, or that frequency band is used to route signals from these movement neurons into LIP. Now, in the literature, gamma activity has been very often associated with sensory processing, and that goes very well together with the observation that visual neurons are associated with that gamma activity. And beta activity in the motor system is very often associated with motor suppression, and we interpret that here, this signal that is linked to these oculomotor neurons in the same way. So if we interpret now this model that I've shown you in this way together with these single unit results that I've just shown you, then what falls out of this is this interpretation. So we think that during the good theta phase, what happens across this network during these rhythmic properties is that there is a state that's been set up that promotes sampling from the environment by enhancing visual processing and suppressing at the same time oculomotor activity. So moving the eyes or moving the focus of attention. Now, during the poor theta phase, when the detection performance is worse, what happens is that sensory processing is less strong, and at the same time there is a release of the suppression from the oculomotor neurons. So at this point in time, attention can be shifted or the eyes can be moved. So during that period, we think that shifting is enabled. So what's happening here is basically this back and forth between these two states. One promotes sampling, the other enables shifting. And we think that this is the foundation for the enormous flexibility, the cognitive flexibility of attention function, that we do not have to log into a state, the state of sampling, to take in information and then get out of that state and get into a shifting state if we want to explore new things in the environment, or we have a salient event in the environment that we need to respond to. But we can do that on the fly because we get basically every 250 milliseconds the opportunity to shift attention. Now, let me summarize briefly my this part of my talk, and then the entire talk. I showed you that attention function unfolds over time and has rhythmic properties. So it's not stationary or static over time, it's very dynamic. Theta oscillations organize sensory and oculomotor networks into two alternating states for sampling sensory information versus shifting attention. And we think that these rhythmic properties account for the flexibility of the selection process. Importantly, we see this both in non-human primates as well as in the human brain. More broadly, cognition unfolds over time. We do not think that attention is the only cognitive function that has rhythmic properties, and this is despite our subjective experience. So I think people already start to look at other domains such as working memory. And of course, we know from long-term memory that oscillations play a major role. We arrive at a new attention model. We see that theta rhythms organize fronto-parietal interactions into these two attentional states that are predictive of behavior. And we also think, and that is something that's speculative, but it needs to be determined and explored in the future, but we think that attentional rhythms may be a hallmark of healthy cognitive function and may open a door to look at conditions like attention deficit hyperactivity disorder or other attention deficits that may result from dynamics that are not properly set up, if you like, in this network. And with that, I want to thank all my collaborators and funding agencies and you for your long attention span.
Yeah, thank you, Professor Kastner. Very excellent work. So maybe we can discuss. Dr. Pan, what do you think about Professor's lecture, the parietal gamma activity and the frontal beta activity, coupling with state rhythmic activity? What do you think?
Yeah, I think it's a very good work, and I learned a lot. But there's one question. I'm wondering that have you ever tried any neuromodulation tools to manipulate or disturb the gamma activity or alpha activity to see what happened on the theta phase, to confirm this? Have you ever tried? I'm wondering that.
Yeah, that's a great question. We have not tried neuromodulation yet. So that is something that one could do in non-human primates, obviously, but we are not yet there, I think, with the tools that we have, because they are probably not specific enough. But this is something that I think will be possible during the next 5 or 10 years for sure. And I would love to look at cholinergic mechanisms in deep brain structures like the thalamus, which may play a really important role here. But just to share that with you, we are doing right now causal experiments so that they are basically a step towards that, because if theta phase is really predictive of behavior, like these correlation analyses suggest that I've shown you, then you would also think that you could interrupt with behavior at certain phases more favorably than at others, right? And we are right now setting up experiments that will use a closed loop stimulation approach to causally interfere with theta, or also to, facilitate, behavior that would be a possibility too. We don't know really what expect, but that is our goal, to develop a closed loop stimulation approach to probe this model that we have causally.
Okay, thank you.
Dr. Paul, do you have any comments?
Yeah, first of all, thanks for this really nice talk, Sabine. It was really amazing. I mean, I know you didn't want to talk about alpha, the alpha effect in the bad.
No, I didn't have time. I would love to talk about it.
But I found that really, really intriguing, because it really makes sense if you say that the bad phase, so to say, is a window where you can shift your attention then, and then the idea would be, I guess, that alpha activity would block incoming visual information, right? Would be the interrupting mechanism which allows going away from what you are just focusing on. So that is really very intriguing, because especially if you consider that quite often alpha amplitude itself is associated with shifting of visual attention, where it would basically be something like, or be discussed as a correlate of disengaging, let's say, a hemifield or something like that. Then in this case, in the mechanism that you explained, it has got a much more refined and much finer scaled function, right? So this is something that I really like.
Yeah, so can I just probably comment on that briefly, because there's a whole story to that again, I just, due to time constraints, I didn't have really time to get into. But one thing I would like to say is that, yes, this goes really together with this visual suppression hypothesis of alpha, because it would make sense that during that period of time, or that attentional state where you do not take in as much sensory information from the environment, you would have a strong alpha if the suppression hypothesis is correct. So that goes really well together with that. But we have also elucidated what that alpha, or what the function of that alpha is, and that is really, really intriguing. So basically, we have a whole line of research that has also looked at the pulvinar, so a thalamic structure in this network, so in this fronto-parietal scenario, and be recorded simultaneously from the pulvinar in these studies too. And what we see there is actually that the transthalamic pathway is basically promoted during that sampling state. So you get a very, very strong alpha connectivity from the pulvinar to the cortex during that state. And we think that goes together with, a hypothesis that this transthalamic pulvinar cortical pathway is a gating pathway for visual information. The interesting thing is that this pathway during the poor phase is shut down, and that alpha signal, the very strong alpha signal that goes from parietal cortex, not from frontal cortex, it's characteristic for parietal cortex, to the pulvinar, and we think the function is to shut this pathway down during that state. So this, alpha signal that we see over parietal is probably a signal that regulates this transthalamic pathway, and basically helps to, to open and shut it down. So there is a mechanistic concept behind that I would hope my human colleagues will embrace more, because we learn more and more about it. And so this cortical alpha may have really an important function in regulating that transthalamic pathway.
Cool.
Okay, thank you. Maybe we can have, if we have time, we can discuss later. And so next, Professor Paul Sampson, he will give us a lecture about the slow rhythmic brain activity during coordination of cognitive process. So, Professor, please.
Okay. So first of all, Yuping, thanks for putting the symposium together. It's really very exciting, and thanks for giving me the opportunity here to present some of our newer data. So I will talk about slow rhythmical brain activity during coordination of cognitive processes. Actually, I'm not moving very far from Sabine's talk. I will also be very much theta centered, so to say. Maybe as a starting point, I show you a short video clip. You might know this chap. He holds the world record in juggling 3 Rubik's cubes, and by juggling them, or while juggling them, he's also solving them. So, which is quite an achievement, I would say. However, our brain is doing something very similar all the time. So there are a lot of different things to do in parallel, a lot of different cognitive functions, processes to be juggled all the time. So if you have, let's say an experimental paradigm like that one, a very simple short-term memory task where, let's say, you have 3 different shapes. One of them is a target shape, and you're supposed to retain this target shape and then mentally flip that and compare it to a probe item or so, then it's actually not a very difficult thing. However, what we have to do during this task is you have to have attentional control, you have to select a target, suppress some distractors, you have to store this information in short-term memory, retrieve it, you have to mentally manipulate this information, maybe also have some control over task event processes and so on. So there are really a lot of different things to do. Now, there is the idea that there's a multiple demand network in our brain, which is exactly for that. So a distributed brain network, a cortical network mainly, which apparently helps us juggling all these different things and coordinating these different cognitive processes. And it's interesting that in a lot of studies, the medial prefrontal cortex seems to be one of the prime players in this network. And activity from the medial prefrontal cortex apparently can also be acquired with the human EEG. So, for instance, when you have a task with different levels of complexity, then what you can quite often find is increased EEG activity in the medial prefrontal cortex when complexity is going up. And usually we find that in the theta frequency range. So a frequency range around 5 Hertz, as we already heard earlier. Quite often what we find in the human EEG, that is a display of, let's say, the head from above. So that would represent the nose, ears would be somewhere here. And that would just be a topographical map of the surface EEG. What you can usually find is that this theta activity comes up really strong in amplitude over these medial frontal electrodes. So the so-called frontal midline theta activity. So around electrode AFZ or FZ, something like that. And it's really something that you usually find becoming stronger and stronger the more complex a task becomes. And just to convince you that this is a quite stable finding, these are unpublished results that some of my first year psychology students recorded. And they recorded EEG while participants were doing a short-term memory task, either one back or a 2 back task. Well, of course, the 1 back task is a very simple one. You only have to press a button when a number is repeated. When you have 2 back, you have to press the button whenever the same number was presented 2 digits earlier, meaning that, of course, you have to regularly update your working memory, your short-term memory now. You have to store more information and so on. It's just more complex, this task. And even this group of students, they very reliably found that when you have a more complex task, then frontal midline theta activity will be significantly higher. So the next thing that we were interested in, this still from a pilot study and unpublished, is whether you could actually interfere with that. So whether it would be possible to entrain this frontal midline theta activity, and by doing so, by increasing the amplitude, increase behavior in, let's say, an MBEC task. So what we did was we used transcranial alternating current stimulation, where you apply a very weak alternating current, and we put the stimulation electrode over this frontal midline electrodes, so FZ, and the return electrode under the chin, so that the trajectory of the electric field should pass through the medial parts of the prefrontal cortex. And then we stimulated either at theta frequency, or we applied sham stimulation, where effectively the stimulator is shut off. And what we found was that in this task, D prime as a sensitivity measure was significantly increased in the frontal midline theta tax in the AC stimulation compared to sham stimulation. So it seems as if this effect is even of causal nature, right? But the question now is, why? Why is there an increase in frontal midline theta activity? Why is it important to have a lot of theta, high amplitude theta in frontal cortex when a task becomes more complex? And the idea behind might be that, as we already heard earlier, the phase of this rhythmic fluctuation is really, really important, that it reflects something like a rhythmic fluctuation in excitability, for instance. It has been shown for theta, but also for alpha activity, that there's a relation between the instantaneous phase of these rhythmic processes and neuronal firing, so that you have a more excitatory phase. In this case, the peak phase would be associated with less activity, and the trough would be associated with increased neuronal firing. Or it has also been shown for theta activity, where you have an association between high frequency bursting and ongoing theta activity. And this has even been shown across different regions, so that you, for instance, have hippocampal theta activity being associated with hippocampal high frequency activity, but also this high frequency activity being aligned to theta activity in the cortex, for instance, like here. So it seems that this increased amplitude in these slow frequencies is necessary in order to get a really big difference between the more excitatory and the more inhibitory phase that is associated with neuronal activity. So we wanted to follow up on this idea, whether this frontal midline theta activity in visual working memory with different complexity is associated with this kind of interregional coupling of slow frequencies and fast frequencies in a different brain area. So what we did was young healthy participants performed this kind of visual working memory task, in which in each trial such a matrix was presented, and then either one or four items or four positions were highlighted in color, and participants had to retain these positions for 2 seconds and then compare them to a memory probe. This was when the items were shown, or these positions were shown in green. When they were shown in red, however, participants did not only have to retain this information passively for 2 seconds, but what they had to do was they had to mirror this information around a little gap in the matrix. You can hardly see it here. But this means that, for instance, they had to mentally flip this element to this side here, while they were also retaining the information and then comparing them to a probe item, which is still quite easy when you only have one item. But when you have to do that with 4 items, it becomes actually quite difficult and quite complex. As one would expect, the 4-item manipulation task, of course, is the most difficult one. only retaining one item is very, very easy. It's not very surprising. We then analyzed surface EEG during these 2 seconds where participants either had to retain or manipulate information. And what we found, and also were not really surprised about that, was that with increasing difficulty or complexity of the task, there was also a very strong increase of frontal midline theta activity. So again, you can see that here over these frontal midline sites, we have a very nice increase of theta amplitude. But now the question was whether this activity had to do anything with activity, let's say, in visual areas, because it's a visual working memory task. So we would not expect that, for instance, the prefrontal cortex, the medial prefrontal cortex, was really involved in the storage of this information alone. So what we did was we wanted to see whether this frontal midline theta activity was associated with posterior gamma activity. We did that by estimating frontal midline theta phase, and then at the same time looking at the amplitude envelope of posterior gamma activity. And then we were just sorting the posterior gamma amplitude according to frontal midline theta phase. So if these two were not related at all, you would expect that the distribution of gamma amplitude as a function of frontal midline theta phase would be completely flat, right? If it looks a little bit like that over here, then this would suggest that you have a very strong relation between frontal midline theta phase and posterior gamma amplitude. Okay, and what we found was a right temporoparietal electrocluster in which in all 4 conditions, we found significant modulation of gamma amplitude by frontal midline theta phase. Now, the interesting thing, however, was that depending on the difficulty of the task, the preferred theta phase, the preferred frontal midline theta phase of this gamma activity over here was different. So that in the more easy conditions, this gamma activity here was nested closer to the peak of frontal midline theta, whereas it was nested closer to the trough in the most difficult conditions. And purely as a speculation, we interpreted this pattern like this. So if you consider that this posterior gamma activity is somehow a signature of increased neuronal activity, then we would have a fluctuation, a pulsed fluctuation of neuronal activity there, right? At the same time, if we consider frontal midline theta activity as a marker of fluctuations of excitability as well, then we would have 2 different patterns. One in where, when we, for instance, consider the results by Saskia Hachens and so on, who suggests that the trough would be associated with decreased neuronal firing, increased neuronal firing, and the peak more like with the inhibitory phase, then if the task is really, really easy, would have a pattern where neurons are more likely to be active in the frontal cortex when there is silence in the posterior areas and vice versa. So in this case, this really, really easy task where it is not really necessary to recruit a multiple demand network, you would have a pattern that looks like active decoupling, making it in fact impossible and nearly impossible for neurons in the temporoparietal cortex to be active at the same time when you have increased activity in the medial prefrontal cortex. Whereas when it becomes really difficult, so that you have to recruit this multiple demand network, when you have to juggle a lot of different things at the same time, you're just nesting this posterior gamma activity in a different theta phase so that you have increased neuronal activity in posterior cortex and medial prefrontal cortex pretty much at the same time, making it more likely that you have some communication within this fronto-parietal network. So we wanted to follow that up with a combined TMS EEG study to see whether this is really a causal mechanism that we identified there. So what we did was we had participants doing this most difficult condition, the load 4 with manipulation. And then within these 2 seconds, where they had to retain information and mentally manipulate them, we delivered a TMS triple pulse over the center of this right temporal parietal cluster with TMS. So in each single trial, we jittered the onset of the TMS. And then at the same time, we recorded EEG and estimated frontal midline theta phase at the time point when we delivered the TMS pulse. So what we did was we simply sorted all the different trials according to the frontal midline theta phase when posterior TMS was applied and looked at behavioral differences. And this is just a reminder of the pattern that we found in the EEG experiment. Remember, we had posterior gamma activity being nested or coupled close to the trough frontal midline theta phase. And this is now the behavioral modulation resulting through the posterior TMS as a function of frontal midline theta phase. So when, just by incidence, we delivered the TMS pulses close to the trough of frontal midline theta, participants dropped close to chance level, whereas they were fairly unimpaired when we stimulated close to the peak phase of frontal theta. So that actually matches quite well the results from the EEG experiment. So just to convince you that this is not very specific for this particular paradigm, this is data from a recent pilot experiment where we had always a fixation cross presented to the participants, and they had to fixate on the fixation cross. Then there was a cue presented pointing either to the left or to the right. And this was followed up then by Garbo batches presented in the left and the right visual field. Then there was a delay phase where we again applied a TMS pulse. And this was followed up with a probe item, either in the cued visual field or in the uncued. So in 80%, the probe item was in the cued visual field, and participants had to determine whether the orientation of the Garbo batch was the one in the memory set or not. So what we did during the delay phase was that we either stimulated with a single pulse over the right or the left parietal cortex. And again, we recorded EEG while we delivered TMS and estimated frontal midline theta phase at the time point when we delivered the TMS pulse. What we found was that when we stimulated the left parietal cortex, there was no effect whatsoever. However, when we stimulated the right parietal cortex, we found that there was a significant modulation of behavior based on at which theta phase, frontal midline theta phase, we delivered the TMS pulse over right parietal cortex. When we hit the parietal cortex at the trough phase of the prefrontal of the frontal medial or the frontal midline theta, there was a significant decrease in performance, but only when we had a trial where the contralateral visual field was probed. However, when the right items had to be prioritized, we did not find a decrease in performance. If so, we even found a slight increase. So similar to the study before, we had a selective effect really only here at the theta trough, which seems to be the important one in this frontomedial to posterior interaction. So, and as a last study, I just wanted to show you that it seems that this frontal midline slow oscillation is somehow related in a function that switches between different networks. I mean, even here, it seems as if this frontal midline theta is switching between the left or the right parietal cortex, maybe, depending on whether information which is processed there is relevant or not. In this study, we again did a visual working memory task where participants had to retain the configuration of such a domino tile and then retain that for up to 6 seconds and compare them to probe stimuli and select which of the probe stimuli was matching the sample stimulus. And we did the task in young, healthy participants and compared them to elderly participants with an average age of, I think, 67 years or something like that. What we found there was in the delay period, not frontal midline theta, but funny enough, we found frontal midline alpha activity. So a little bit faster than what we are usually expecting. However, all the other features were exactly the same thing as we would usually find with frontal midline theta activity. So there was again an increase with complexity, with working memory load, and also the location was very similar. So it seems that depending on the task, really, it might either be a little bit faster or a little bit slower. They are very, very close in the frequency spectrum, one also must say. But what we also found was that this frontal midline alpha phase was associated with amplitude in the gamma frequency range, in the precuneus, and in the right intraparietal sulcus. So the right intraparietal sulcus seems to be quite important for retention of material in visual working memory, right? So that makes total sense. That is basically a region that seems to be task relevant. The precuneus, on the other hand, has been associated with the default mode network. Is one of the key players in the default mode network. And now again, remember that for alpha activity, there has been the report that the trough is associated with more excitatory activity and the peak is associated with more inhibitory activity. And if you then look at the pattern our young participants showed, you see that the precuneus, as part of the default mode network, seems to be coupled to the more inhibitory peak phase of frontal midline alpha activity, suggesting that you again have this kind of mechanism of decoupling, of active decoupling of the default mode network in this case. On the other hand, the task relevant region, the right intraparietal sulcus, is coupled to the more excitatory trough of frontal midline alpha activity. And now the interesting thing is that the elderly participants show exactly the reversed effect, where they have the precuneus coupled to the more excitatory trough and the task relevant region to the peak phase of alpha. And the exact individual phase where this precuneal activity was locked to on an individual basis was also predictive for task accuracy and response time. So what you could say, taking all these different studies together, is just jump over that, is that it seems as if the frontomedial cortex, the prefrontal cortex, and the slow activity over there works like a switch between different networks, depending on whether you have to couple a frontoparietal network or actively decouple this network. You would nest sensory activity, posterior activity in a more favorable or in a worse phase of this slow oscillation in order to achieve this coupling or decoupling. And it seems as if you can even switch between different networks with this particular mechanism, making it possible to, for instance, then disengage the default mode network and engage a task relevant network, or if that does not work, like in our elderly participants, this might lead to difficulties with short-term memory capacity, for instance. So it seems as this mechanism that I just described is a mechanism that is important for dynamic cognitive resource allocation and for prioritization of information processing. It's a very dynamic mechanism, so to say. And with that, I want to thank my collaborators, especially Barbara Berger and Birgit Griesmeier, who were associated in this working memory study that I presented. Annalena Biel has done a lot of the piloting studies, and Diego Pinal was the main author in the aging study. And then I also want to thank the people who pay for all that. Thank you.
Yeah, thank you, Paul, for giving us an idea about the fronto-parietal coupling. So, any comments from you two speakers?
I think this was really fascinating, Paul. Thank you for this very clear and really interesting talk. And I think it really worked together with what I presented in many, many ways, because I think what emerges from here is that these slow oscillations in the theta and alpha range play this role of orchestrating networks that could happen. I've shown that within a network where you have subnetworks that are in functional conflict. You have shown that across cognitive domains as the switching function. And I think this is a really important kind of emerging functional concept, because it's a big question how cognitive networks can get integrated, how cognitive function can be integrated, because we do so many things, as you said in the beginning of your talk, at the same time cognitively. And these things are performed by very specialized large-scale networks, and how can they so seamlessly, work together? And I think these slow oscillatory signals that we have in the brain can play that role. And one question I have for you, and this is just a speculation, I believe, but I'm just curious what you think about that, is where if there is basically a central generator or a few central generators for this kind of activity, or are there a lot of local generators, and how then would they be, orchestrated? So how do you think about that?
Yeah, is a tough question, especially when you're working with surface EEG, right? So it's not really the best method for dissociating different generators. Maybe that generators that are quite close by. But as a speculation, I would assume that there should be a lot of different generators there, also at different frequencies, right? Depending on the size of a local network. And that might also help in dissociating different systems. So what we, for instance, find is that this frontal midline theta activity is localized a little bit further caudally in tasks that have a stronger motor component, and more rostrally when it becomes really high cognitive, right? So it seems that there are different areas that are, slightly slightly specialized and might also resonate at a slightly different frequency. So, I mean, a good example is also that we found a very similar result in the last study, just at a frequency slightly higher, right? In around 9 hertz or so, instead of 5 hertz where we find it usually. So this might also be an indicator that it is not the same generator in different tasks and for different networks, that we have kind of specialized networks that are coordinated by a particular driver, but that we have different frontal mechanisms than for, let's say, short-term memory, for rather motor or sensory motor tasks, or maybe decision tasks or so. So that would be my guess or my hunch.
Dr. Pan, do you have any comments?
I think it's very quite new results and something different from the traditional I think result. Like with sometimes in the literature it is reported that the working memory is also related to the dorsal prefrontal. So in this I think, but in the basic neuroscience, I think it's your result is very consistent with the basic neuroscience. But there was one question is from the poster high frequency to the anterior, I think it's a slow frequency. Is there, especially when the TMS at the right of the posterior, is there any difference between the left hemisphere and the right to the frontal midline?
Mm-hmm. So in this first study, we only found the right posterior gamma activity being modulated by the frontal midline theta activity. There was nothing in the left hemisphere. So we only stimulated in the right hemisphere. In the second study that I showed, we did the left and the right hemisphere, so delivered TMS in left and right parietal cortex, and we only found an effect in the right hemisphere. Actually, I would have expected that we find exactly the reversed pattern in the left hemisphere. That did not work out. But also one must say that we did only use a few participants. It's a pilot study, so it's I mean, even the effect that we have, I would not trust it too much, right? Because it's a very small sample and it's not replicated internally. Whereas the TMS study in the first in the first study that I showed, we did it actually twice and did an internal replication and found the consistent pattern there. So I would trust that a little bit more. But I would guess that if, for instance, the verbal component of the task was a little bit higher, that one might get a shift towards the left hemisphere. So that is really only because we are studying visual working memory that we have this bias towards the right hemisphere.
I see. Thank you.
Yeah. Okay, let's move on to to our last speaker, Dr. Pan. She'll give us a talk about the neurobasis of numeric and arithmetic calculation in our human brain.
Okay, it's my great honor to present our group's recent work to Professor Catherine and Professor Thorson. We hope we can get some valuable suggestions from you too. And our group's work is focused on the posterior gamma to anterior beta coherence mediates numerical mental arithmetic in human brain. We know mental arithmetic is a complex cognitive activity which is consisting of different processes, including the recognition and the comprehension of the numbers and the memory processing, like the numerical comparison in subtraction and performing the mathematical calculation and the later activities like remembering the result, decision making, and even maintaining the attention. And several techniques are used to explore the arithmetic process, like the functional MRI and scalp EEG, subdural intracranial EEG, And even the event-related potential studies is used to explore this process. However, a specific electrophysical logical marker as the neural basis of numerical processing and the mental calculation has yet to be identified. And we know that literaturely, the functional MRI result have showed that the many brain subregions are involved in the number comparison and the mental calculation, like the natural parietal cortex and the ventral temporal cortex, even middle frontal gyra, and even the intraparietal sulcus. And recently, an EEG study showed that number form area in the posterior inferior temporal gyrus has been specifically implicated in the process of the numerals. And our groups also find some ERP component is related to the number compare region. So even some brain regions are also confirmed to the common neural subtract in both the number processing and the calculating. So our studies aim to solve the neural process of the complex operation like the subtraction. So to figure out how the neural basis of the mental calculation, we use the stereo EEG to carry out our studies. And the intracranial encoding were obtained from the 20 patients with the pharmacological resistant epilepsy at Xuan Hospital. And in our study, the experiment is divided into 2 tasks. And we can see the participants are required to finish the delay match to sample paradox. And the task 1 we call the perceptual mismatch task. The subjects are required to judge S1 and S2 are the same or different. And if there are 2 conditions, for condition 1, the S1 is the same with S2, then the subject will answer yes. Press the keyboard to answer yes. And for condition 2, S1 is different from S2. And for in task 2, we call the calculation task. The subject are required to judge S1 minus S2 is equal to 3. For there are also 3 conditions. For condition 3, S1 minus S2 is equal to 0. That means S1 is the same with S2. And for condition 4, S1 minus S2 is equal to 3. The answer is yes. And the last condition, S1 minus S2 is unequal to 3 or 0. So the SEG, so we screened excluding the epileptic firing recording site. We screened out totally 348 recording sites distributing in the 5 cortical lobes and the limbic region, as the SEG amplitude is displayed as the heat map. We can see in the 5 conditions, and in the and also to reconstitute all the recording sites, we correlate the post implanted CT images to the pre-surgery MRI to obtain all the MNI coordinates of each recording sites. And we defined these coordinate sites according to the Human Brain Nectome Atlas, which is published in the cerebral cortex in 2016. And we can see all the 348 recording sites are distributed in the subregions, which shown in the table at the right panel. And for this task, the behavior results show that all the patients finished the task with a very high accuracy, and the reaction time showed a very typical, I think, very typical properties of the numerical cognitive activities. That is the problem size effect. That means the behavior data indicated the degree of the difficulty of the subtraction problem. And we also did some correlation analysis, showed that there's no significant correlation of the gender or age of the subjects to their behavior data. So back to the SEG result, we got the amplitude. We compared the amplitude, SEG amplitude in situation of the S1 is the same with S2 versus the S1 is different from the S2 in task 1 and in task 2. And we got the P-map of the p-values, and the red p-values showed that the significant p-value is less than the 0.005. So we can see, and we cluster all the p-value. We cluster all the p-value using the k-means method. So we got 3 clusters. And according to the publications, that we know that when the brain processes the incongruity information, and the ERP, one of the ERP marker that happened at the negative 200 milliseconds after the S2 onset. So we are focused on the cluster 1 at the middle panel. We can see here the difference occurred around 200 milliseconds after the S2 onset. We are focused on these clusters, and all the recording site distributed in these clusters are shown as here. And we can see that the dotted line is the ratio of the recording site of the totally site. So we are focused on those histogram above on the dotted line, and we analyze the common part of the recording site, both in the 3 clusters that are closely related to the numerical incongruity processing. So we screened all the common regions. We got 15 core recording sites that is responsible for the numerical incongruity processing, which are distributed in middle frontal gyrus, supramarginal gyrus, and angular gyrus, and in inferior and middle temporal gyrus, no recording site in the occipital lobes, and 2 subregions in posterior insular, and a high proportion in the ACC. All the recording sites are showed in the templated brain. So we want to know that what happened between all these recording sites. However, it's very difficult to get all the recording sites in only one subject. Fortunately, we got 3 recording sites in only one subject, that is supramarginal gyrus, posterior insular, and inferior temporal gyrus. And we analyzed the correlation between each 2 regions, and we compared the 2 tasks, 2 conditions. One is S1 is the same with S2, and S1 is different from S2. We can see that the EEG amplitude correlation coefficient showed that between supramarginal gyrus and inferior temporal gyrus, there are no significant difference between the coefficient in 2 situations. However, in the other two cases, like between posterior insular and and supramarginal gyrus, and between posterior insular and inferior temporal gyrus, when S1 is the same with S2, the coefficient between the two regions are negative. And however, when S1 is different from S2, the coefficient is positive. It is positive, and we're using the chi-square test. There is significant difference, and to show and to figure out the and to confirm this result, we also analyze the signal in the frequency domain, and we screened the 6 conventional band like delta, theta, alpha, beta, gamma, and ripple. And we found that also during this time lapse, I forget to mention that only during this time, like 195 millisecond to 275 millisecond, there was a significant difference. And we screened all the conventional band that we found only in gamma band, the coherence in the post-insular and inferior temporal gyrus. We also can find that the coherence have a very significant difference between the two situations, like S1 is the same with S2 versus S1 is different from S2. So it is suggested that the gamma band coherence in the two regions might mark the numerical incongruence process, and this result also confirmed by the result analyzed in the calculating task. We also can say that when we compared the S1 is the same with S2 or different from S2 in calculating situation. Also, the core region mentioned above are also indicated here, and the incongruent information exists a great extender like the frontal region also in the calculating incongruent processing. Besides, we showed the insular and limbic regions. And also in the calculating task, we can screen the 6 regions, that is specific regions involved only in the incongruent processing in mental calculation rather than the incongruent processing in perceptual mismatch. Like the resulting equal to 3 on unequal to 3, this incongruent processing. These 6 regions are responsible for the calculating incongruent processing. So after we figure out the neural basis of numerical incongruent processing, we move on to the subsequent calculating part. We also use the similar clustering method to cluster the p-value under the different situations. Like this is the S1 is the same with S2 just under the task 1 versus the task 2, and the last 2 situation is the S1 is different from S2 under the task, also under the task 1 versus task 2 to discriminate the mental subtraction process. And we also get the 3 clusters, like here, the first 3 clusters. We can see that the first class, the difference occurred just as soon as S1 onset, and all the sites in the cluster 1 are distributed in temporal, parietal, and frontal lobes. And the class 2, we can see the difference occurred later at around the 200 milliseconds after the S1, S2 onset. And in this situation, we can see that insular lobes are involved in this part. And in the third cluster, we can see the different occurred just after the S1 duration. And we can see the common recording sites are only temporal and insular, located only in temporal and insular part. And also we found the common recording site in two patients, like in the patient line 15, we can find the pericentral lobus and postcentral gyrus in the one of the subjects. And we can find the recording site inferior frontal gyrus and anterior insular in another patient number 16. Also, we analyze the gamma coherence in the two subjects. We can see that in the first subject, we can see that during the 260 to 390 millisecond, just after we showed the gamma coherence we mentioned before. Here we can see also the gamma coherence between the pericentral lobus and the postcentral gyrus. The coherence coefficient is significant different between when the S1 is the same with S2 under the calculation, and here is the S1 is different from S2 here. And also in situ of these two regions, the gamma coherence transfer to beta coherence during the time of 550 to 450 to 560 millisecond is a significant difference between of the beta coherence. And then after that, during the 470 to 570 millisecond, the beta coherence in inferior frontal gyrus and anterior insular, here is quite significant difference between the two situations. So to summarize the result, we can see that from our result, we can say that the post-insular and inferior temporal gyrus coherence in gamma band would function as a marker of the numerical incongruity processing, and the gamma band and in the pericentral lobus and the postcentral gyrus, the gamma coherence shift from the beta coherence at the location, which is maybe response for the mental calculation. Then the gamma beta and the beta coherence in inferior frontal gyrus and anterior insular might indicate a later processing, including the decision making. So that is our group's work, and thanks for attention. Any suggestions and advice are very welcome. Thank you.
Yeah, thank you, Dr. Pan, for your very excellent work, but a little complicated work. And so, Professor Kastner, do you have any comments?
Yeah, probably along the vein that you just mentioned. It's very complex work, but once you get into let's say human-specific abilities, things do get a little bit, or tend to get a little bit more complex. So with numerical cognition, that is certainly the case. My question that that I have for you is something that I think we all struggle with, all people who study cognition, when it comes to more complex tasks, and that is, how do you equate for all these different task components, like differences in task difficulty that will lead to differences in attentional or in allocation of attentional resources, for instance. And we know that those will, change, modulate brain activity in different ways. How can we deal with that? I asked that more so because in at least some of your tasks, you had ceiling performance, so you cannot really look at that very well anymore. You have reaction time differences, but the accuracy is at ceiling. So how do you deal with that?
Yes. I think the task attention is a very important disturb in our situation. For this, so we use the comparison. Here we can see that we only compared the two situations in one task to remove the task attention disturbing. You can see in the figure A1, they are only in in the same task. We compared the two situations, and we can see also that we can see this class the cluster 3. We can see the cluster 3. The different occurred just we can see the different occurred very early. I think this site in the third cluster maybe maybe involved in some attention or the focusing the task. So we just exclude this recording site. And also in our calculating analyze here, we also can, I just mentioned, because the time limit, we just mentioned the first 3 clusters. We can see the last 3 clusters also the difference occurred very early. You can see there's no time loss variety here in 3 situations. So maybe those recording sites are related to the attention or something. Just that's what we want to exclude it. And those just very pure result only related to the calculation we want to give our analysis here.
Thank you.
Dr. Paul?
Yep. Thanks for this really nice talk now. It's really fascinating. And I really like the approach of using a cluster analysis here to reduce down or break down the complexity of the data and select the particular time windows and sites and so on. Is really very, very neat. I've one question, because what you find is sometimes a difference between, for instance, comparing the identity of 2 numbers and subtracting the numbers with a result of 0. So basically, it's the same thing, right? It's S1 and S2 being exactly the same. But in one condition, you have to say whether it's the same or not. And in the other condition, you have to say whether the difference is 0. So actually, it seems very similar, but still you get a very clear differences in gamma coherence. So my question is, do you think this is because you are, as a participant, you're in a completely different mode, so that you judge the stimuli completely differently, so that when you just have to say whether they are different or not, it is a more sensory task, whereas you are in a more, let's say, arithmetic mode or something like that in the second task? Or is it that you have a mismatch of the time windows? Because if you are, or it could also be a combination, if you're doing the arithmetic operation, It just might take a little bit longer, right? You would also say, okay, number 1 and number 2, they are the same, but you still subtract them and say, okay, it's 0. So you might have a temporal delay, and then in your analysis, it comes out as a difference. So do you think it's just a mode, or is it a different temporal dynamic, or a mixture of those? Yeah, like here, for instance.
Here, you mean that the calculating may be mixed with the numerical incongruity processing?
Yeah, for instance, in let's say it's very small here, but if you compare the two numbers, right? So for instance, the first line compared to the second line, right? In one, it is kind of bluish. In the other one, it is kind of reddish. And it looks a little bit as if in the second line, you just have a stronger delay, right? So that the red blob comes up a little bit later compared to the first line. So might it only be a difference in temporal dynamic, which also might be really nice, because this means that your gamma coherence would basically trace the temporal dynamics of cognitive processes, right? Or is it really a state dependent?
I use a 50 millisecond frame where to shift with every 10 millisecond to do the chi-square analysis. So only this duration have a significant.
Yeah. Yep, it's nice.
Okay, so I think maybe the calculation is not so. It's a very complicated processes, maybe very sub processes. So you can do it to analyze each sub processes according to the tasks, maybe. Okay. Anyway, you give us
sorry. And we think the parietal to frontal region is a very critical hub in this calculating processing in human brain. We think.
Maybe so. So this is just in the so Professor Kastner's talk. Professor mentioned the gamma activity, posterior gamma activity, and the frontal beta activity. So, do you think the Dr. Pan's work, the gamma beta shift from the posterior insular to the anterior insular is related with what you found in your attention task?
I don't know, but I think we need to go. This is just more a general statement here, because I really can't speak to that. I have, no experience with the kind of experiments that you do in numerical cognition. So, those would obviously also not be possible to do in monkeys. But I think just in general, this is a really, really important thing for me. I think we as a field need to go away from labeling this is beta, this is gamma, and all gamma frequencies are the same. They are not. Gamma frequency bands are embedded in circuits, and it depends on that specific circuit that is recruited. I would strongly assume that the circuit that now recruited is different from the circuit that I have studied. There may be overlapping parts, but the overall circuit is for sure different. And I think we need to discuss gamma activity or beta activity or whatever, theta, it doesn't matter what frequency band is in a specific task and in a specific circuit. But we need to go away from labeling as if, you know, they have a function per se. They do not have a function per se. They are more, you know, frequently associated with certain functions. But again, depending on the circuit that they are embedded in, gamma activity could have a memory function, a sensory processing function, et cetera, et cetera, et cetera. And I think we need to be much more specific in our field, what we are talking about it. But I don't like to talk broadly about gamma, beta, or whatever.
Okay,
so that's more of a general statement.
Yeah. So
may I comment on that? I totally agree with you, Sabine. Because I think that the worst thing we can do is trying to match particular frequencies with particular cognitive functions. That just doesn't work, right? And also even being as broad as saying like a particular oscillation, like let's say alpha activity, is inhibitory and and another one is excitatory or so. I would say it also doesn't make sense, because for the brain, why should it be different for different frequencies, right? So I mean, it's just generated by the different parts of the brain and by the different circuits, but the basic function of rhythmic fluctuations should be exactly the same across all the different frequencies. I would assume, at least. So I think this is really something that we have to overcome this tradition of labeling these different frequencies and trying to match particular cognitive function with them. So I totally agree with you. Yeah.
It's almost like a modern form of phonology in a sense, you know, to do that. And we need to go away from it.
Okay.
Exactly.
Yeah. Okay. So due to the time limit, have to close this session. Today, three excellent speakers give us a full discussion about the fronto-parietal networks, especially about the role, the participation in the working memory or the attention task, and at last the calculation task. So in the future, maybe in the next few years, we can do much more detailed study about the fronto-parietal networks function. So hope to meet you again in the future meetings. So thank you.
Thank you very much, Yuping, for organizing this. It was a real pleasure.
Thank you.
Thank you.